Yeah, as you can see on this first slide, it's a very general topic. Basically, I want to explore with you or look at some of the results that we obtained in the context of exploiting machine learning for first principles calculations. To give you a bit better idea of what this will be all about, what I have been concerned with in the past years is the question of how accurate quantum chemical calculations are for a given purpose, not at some benchmark set, but for the purpose that you are using them for. And in order to figure that out, you will need rigorous uncertainty quantification. And so we have been looking for a couple of years now into machine learning applications to extract confidence intervals, uncertainties from the machine learning model that was trained on specific data in order to figure out how good the data actually is. Of course, as a theoretical chemist who really likes quantum mechanics, I like to have descriptors and features be based on the first principles of quantum mechanics. And it would also be nice, of course, if the machine learning models are interpretable in the end. By the way, you see a reference here on this first slide, which goes to an archive paper, but in fact, the paper has been accepted by the Israel Journal of Chemistry. If you want to learn more about the basic philosophy, I invite you to have a look at the paper. Before I switch to the machine learning examples that I want to discuss with you, I'd like to point out that we have done, before we switched to machine learning, we have done other work where we extracted uncertainty information based on standard statistical means such as bootstrapping and jackknifing, where we evaluate the reference data sets that are available. For instance, for physical chemical models in general, is an example that we studied was the models that are used to predict Mös-Bauer isomer shifts, but also for D3 dispersion corrections. And I will actually that were proposed by Stefan Grimmel's group, and I will come back to this topic at the end of my talk in the context of machine learning. We used also delta machine learning to improve system-focused self-parameterizing atomistic models. Those are models that construct force fields on the fly, but are also employed in QMMM context. I have no time to talk about them, but I just wanted to draw your attention to these topics before I go into the details of these two topics. So I selected two where we applied machine learning to. And the first topic actually is reaction network exploration, which we do in an error-controlled way. I will tell you all about it in a minute. And then I come back to this topic to improve semi-classical dispersion interactions, which is basically the D3 model. And that will all be based on Gaussian process regression. Sorry for the typo there. And before I start, let me briefly recall what Gaussian processes actually are. So Gaussian processes, as you can easily find on the internet, I will explain that to you, of course, in a minute, is a collection of random variables. So there's an input for which has a joint Gaussian distribution. And you see that there's a covariance function here given in this equation. You see the input variables here, and there are two hyperparameters, sigma and L, given in here. And of course, you need to train this model, and the training affects the confidence interval that you reach. So for instance, say this is the true data given here in red, and you have a single data point, then that is of course not enough to make any predictions. And so you continue collecting data points, and where you have the data, basically the confidence interval, the uncertainty shrinks, and you can exploit the Gaussian process to tell you where in your parameter space that is defined by the input variable, the uncertainty is large, indicating that this is a region where you need actually more reference data. In a more global picture, basically what you have is this. See, you have the data points here, which are the crosses in black. And then you interpolate between the data points. And there's, of course, this input variable. This is the descriptor, which kind of is a measure for the space that allows you to arrange and order your, in general, physical model. In our case, these will be molecular structures. And so between the data points, which are points for which you have high accuracy reference data, you can interpolate with the Gaussian process. And then there will be a region where you don't have data points. And of course, the variance will be big, right? The uncertainty will be large, but this is an indication where to get more reference data. And in fact, this is what we are doing. We calculate reference data on the fly where we need it. And surely this is a very efficient way to have reference data at positions where we need them, so for structures for which we really need them, and a way that allows us to reduce the number of reference calculations, right? We don't have an arbitrary distribution with some arbitrary measure of determining where we do the reference calculation, but we let the Gaussian process determine this. Okay. What are these input variables? Well, what you could use, for instance, are the eigenvalues. This is one of the standard choices of the Coulomb matrix, right? The Coulomb matrix is defined here. It relates to the external potential, and in this respect, it has also a relation to the underlying electronic structure theory. Then there's a diagonal where you get of course, no contribution from the internuclear repulsion, and the Coulomb matrix uses this parametrized diagonal, which turn out to be very useful in machine learning applications. So that is something that you can do. There are other choices. And in fact, for our error-controlled reaction network exploration, we used the SOAP kernel rather than the Coulomb matrix, which is another popular measure for molecular similarity. But before I come to that, let me briefly explain to you what the idea is about these reaction networks. So, and we are talking about networks of chemical elementary steps, elementary reaction steps. This is a way to think about chemical reactivity, that's obvious, but chemical function in general, right? And the problem is that typically you calculate only a tiny fraction of these elementary steps that is potentially relevant for some chemical problem at hand. And you need to explore much more to get an in-depth picture up to the point where the calculations really get predictive. And this is what we are working on. And of course, you can't do that manually because you will encounter thousands of elementary steps. You need to do that in an automated fashion. In order to do that, we have developed over the years a couple of methods. All those methods aim to make standard quantum chemical methods more stable and faster, so that they can be driven by an autonomous reaction exploration program. And this program in our software suite is called Chemoton. Here you see an old version with an old GUI. We are working on a new one, which gives you a rough idea how working with the program looks at the side of the operator. So if you're sitting in front of the screen, and of course, this picture doesn't talk to you, right? It should just give you an idea that exploring reaction networks basically means that you need to crawl across a Born-Oppenheimer potential energy surface. You will visit many structures which are indicated by these colored dots. And from these structures, you can then start decent optimizations of stable intermediates and of course, transition states. And actually, the Chemoton program does this fully automatically for you. To show you an example how that looks in practice on the chemistry side, this is the first example that we actually considered, the Formose reaction. It's considered to be of prebiotic importance because from very simple molecules you can generate sugar molecules, and actually that has all been studied before, so that's why it was a good target for us by Alan Aspo-Gutzik's group. What we did is we did PBE calculations in a double zeta basis. We carried out 150,000 calculations in 2 weeks, no manual interference. That gave us 1,000 unique molecular configurations and 10,000 transition states. And this way, at the time, we obtained the largest network available for the Formose reaction. And this is not the full network. This, what you see here, is a section of the network, just again, to give you an idea of the complexity. The colored dots indicate specific structures, like in blue, you see the starting material from aldehyde and glycolaldehyde. And the sugar molecules are actually highlighted in violet and orange. These are trioses and tetroses. And then, of course, you build up molecules containing more and more carbon atoms, which is indicated by a deeper and deeper green color. And so you see very many reaction steps which are mapped out here for this process. And of course, it's difficult to understand chemical-wise what's going on. But you can design automated algorithms which evaluate this. And then from these algorithms, for instance, you get sub-mechanisms which tell you how, from the starting materials on the left, you actually go to the sugar molecules here in violet and orange. Okay, so this is what we are applying it for. But the problem is, okay, we do DFT calculations, and in the end, of course, we would like to do kinetic modeling. But what about accuracy, especially when you keep in mind that the energies enter exponential expressions in the kinetic modeling? So we need uncertainty quantification because we really need to know how good our data is. Otherwise, we might get the wrong interpretation of the mechanism. But the problem, of course, is that for a specific quantum chemical result, the uncertainty usually you don't know, right? And so what you typically do, and this is not what I'm advocating here, is you compare two accurate reference calculations for a few systems for which you can do these calculations, and you rely on benchmark studies. But the key issue here is that transferability is not at all guaranteed to your specific system, right? And even when you look at the benchmark data that are available, you get indications where from mean absolute errors, which are large even for the benchmark sets, where you have large absolute deviations, which are do not match the mean absolute errors, which are indications that there is some heterogeneity in terms of the error when you look at the data. And that is, of course, not acceptable for really predictive work, right? So what do we do? Of course, I now come back to the Gaussian process regression that you have seen before. And so we would like to exploit such a statistical model and the uncertainty quantification that is provided by the statistical model in order to get a system-specific error estimate that will also tell us, in combination with this molecular similarity measure, like the Coulomb matrix, tell us where we actually need more reference data in order to have better results. I mentioned this a couple of times, so we need a measure that allows you to explore chemical space in a systematic way, and the Coulomb matrix is one option. In this study, we used SOAP. We have seen that SOAP is in our applications is often more reliable than the Coulomb matrix, which I think has been found also by other groups. So this is why we rely on SOAP in this context. And SOAP allows us to tell how similar, actually, given one node in our reaction network, other nodes in the network are compared to this node. And say, if you now have reference data for this node in the center available, you can use the Gaussian process to tell you how much you can say for those molecules which are to a certain degree similar to the one for which you have the reference data. The application that we picked was basically data available from the literature, where we are on one potential energy surface and we have hundreds of structures that can be explored, right? So you can use a cheap model like DFT to study these structures, and then you need reference data to get the uncertainty quantification, and use the Gaussian process to tell you for which of these structures you do the reference calculation. So this is, of course, just a sketch of the many structures that we investigated, and the red dots are those structures for which the Gaussian process told us, please run a reference calculations based on coupled cluster theory. And of course, you could argue, well, coupled cluster theory is a black box method that is reliable only for closed shell structures, right? And that is true because, especially if you go through a reaction network, you will encounter structures that have multi-reference character. And so it's likely that coupled cluster theory breaks down for those structures. And you need something else more general. And of course, a multi-configurational method would be good. But then you face a problem that typically the active space is limited. And also you can no longer run this in a black box manner, by contrast to coupled clusters. So how do you deal with this in a context where you have an autonomous exploration? You see thousands of structures with an automatic launching of reference calculations. So how would you do that for a general electronic structure? And this is the solution that we picked. We use an approximate CAS-SCF approach, which is DMRG, which we, however, can run in a black box fashion, and which allows us to go to active spaces, which I would say cover all sizes that are relevant for reaction chemistry in the ground state. For those of you who don't know much about DMRG, DMRG is basically a CI type method, and you see the CI wave function here on the left, but it parameterizes the CI coefficients in a very special way so that it can be optimized very efficiently with this density matrix renormalization group algorithm, DMRG. Okay. So we have this software that can do the calculations. How do we select the orbitals in order to run this automatically? We do that based on entanglement measures rather than on natural occupation numbers, because we found that these orbital entropy entanglement measures are very useful and very stable for this purpose. Here on the right-hand side, you see the key equations. Basically, these are Shannon or von Neumann entropy expressions where the eigenvalues of a very special reduced density matrix enter. And these are reduced density matrix, not one particle or two particle reduced density matrices, but one orbital and two orbital reduced density matrices. You construct a single orbital entropy from this. This is the first equation. And then something that's called the mutual information, which is computed from the two orbital entropy, where you take the single orbital entropy out. You don't look at the numerical values, but instead you check these orbital entanglement diagrams where as red circles, you see the single orbital entropies, and the connecting lines are the mutual information. The thicker the line, the bigger the circle, the higher the value. And this is an example for the single delta G state of dioxygen, which consists basically in a qualitative picture of these two configurations in this molecular orbital diagram, where the pi star orbitals 6, 7 are each doubly occupied. And you see that in the entanglement diagram. So out of this, you can construct a orbital selection algorithm that runs fully automatically, uses a partial. I don't walk you through the details here, but just the basic principles. Here you run a partially converged DMRG calculation, then you get the orbital entanglement measures from this, because qualitatively the wave function will be okay. And then you do the selection and do a decent calculation. That can be done automatically. We provide a program for that. It's available from our webpage, and we will release a command line interface in a few weeks. Okay, so this is how we exploit the Gaussian process regression in the context of reaction network explorations, but we also looked into electronic structure models. We started with semi-classical dispersion interactions, and so I'll tell you a bit about the results that we obtained here. Now, the idea is to improve on the D3 model by Grimme, because based on bootstrapping and jackknifing, we have found that if you go to increasing molecular sizes, you cannot build upon error compensation. So it can be that these D3 corrections build up error if you go to larger molecules. And in order to improve on this, we want to exploit the Gaussian process regression. Now, for the similarity measure, we exploit the expression of the D3 correction, right? Which you can see here. You see it has two indices. So in a way, you can treat it as if it would be the Coulomb matrix, for instance. And so you can diagonalize its matrix structure here. Use the eigenvalues in the very same way as the input variables for the Gaussian process. And then, of course, you can either go for a prediction of the total dispersion energy, or you do delta machine learning. So the first option is shown here on the left, or you do delta machine learning on the right, where you have a DFT model on top of the D3 correction. And then on top of that D3 model, the total D3 model, you do the delta machine learning through the Gaussian process. Both works fine. We actually are more in favor of the delta machine learning model because that should be more efficient in terms of the number of reference data needed, the amount of reference data needed. Again, we use a Gaussian kernel, and these input variables, boldface X, they are now the eigenvalues of the D3 correction. And then we train the model. We have the hyperparameters that change everything. Of course, we need the data set. The data set is, first of all, a subset of dispersion-dominated cases in the standard S66 data set. And then on top of this, we created reference data ourselves, where we had dimers which are dominated by dispersion interactions of pentane and ethane. And we created very many configurations for these dimers, and then run coupled cluster calculations based on the DLP&O approximation by Frank-Nese. So we exploited ORCO for this purpose. We tried to push it to the basis set limit, and for the DFT calculation, you see we used also pretty good basis sets, and then the standard D3 setting. With the data, we were able to analyze the way we learn with the Gaussian process. So we had our data that can be split into training data and then test data, and so that we can inspect the interpolation capabilities of the Gaussian process, and then we can switch to the subset of the S66 test set and look at extrapolation and monitor the D3 error. And of course, it's possible this way to systematically, in a system-specific way, improve the D3 corrections. In the context of this study, we learned that when you train the Gaussian process, of course, you can do that by random selection from the reference data, right? But we found it to be much more efficient when we do something which we call batch-wise variance-based sampling, where we use the new data points based on the maximum variance. That was much more efficient than doing it randomly. The overall workflow now for this machine learning improved dispersion corrections is as follows, and very, very similar to in spirit to what we did for the reaction network exploration. So we have some, of course, initial reference data for the training, but then generate on the fly more reference data, because we have a query set that...
Oh, hello, Professor Markus Reiher. I think you should speed a little faster. Speed up your talk.
This is my last slide, in fact.
Okay.
Okay, to cut a long story short, we use the Gaussian process to determine whether we need more new reference data for the query structure, and those data we produce on the fly and then improve the model. This is my conclusion slide. So I hope that I've shown you that Gaussian process regression actually is very beneficial for producing error estimates for system-specific improvement of quantum chemical data. And especially I would advocate for this batch-wise variance sampling because that increases the efficiency of the learning process. This is my group working on very many different topics, as you have heard in the beginning. The results that I've shown you were that was work that was done by Stefan Gugler, and also by people who are no longer on this list because they have left the group. And those people are Johnny Proppe, Gregor Sim, and Christopher Stein. Thank you very much for your kind attention and for your patience.